So the next major thing that we look at as an application of this, we've already talked about this definite integral being an area under the curve, but if we wanted to find the area between the curve and the x-axis, well, that's our integral. We've also seen that sometimes our area, that if it's above the x-axis, it's always positive, and if it was below the x-axis, it was negative. So now we do some application questions just with those area types of questions. So find the area enclosed by the line y equals 2x minus 1 between x equals 1 and x equals 5. Make a sketch. So first of all, if we draw that line, that's an easy line, a y-intercept of negative 1, a slope of 2, so rise of 2, run of 1. This is what our line would look like. And from x equals 1 to x equals 5, I've got the point 1, 1, and up here, I know it's a little bit off, but I'll have 5, 9. Imagine those lines are straight. We are looking for that area. Actually, if we're coloring things in, it is way more fun to color with crayons. There we go. You ever seen the Smartboard crayon pen? It's so fun. All right, there we go. It really, I'm telling you, if you need a stress relief, I can put up some coloring pages on the Smartboard. You can come in and use it is so fun to crayon on a Smartboard. I don't know why. It has all of the, notice how some parts are even thicker. Okay. Anyways, so if you need that de-stressing, crayon coloring on the Smartboard, highly recommended. Yeah, I know I'm still recording. Okay. So, we have this picture drawn. What does this mean? This means that we are going to integrate from 1 to 5 of 2x minus 1 dx. So to find that area under that curve, we just integrate this. How do we do that? Well, the integral will be x squared, 2x squared over 2. I'm using the technique rather than just writing it out. If you wrote just x squared because you could see it, that's perfectly fine. But what do? We add 1 to the exponent and divide. Minus x from 1 to 5. The way that we calculate our definite integral is we now plug in 5, then subtract and plug in 1. So plugging in 5, this is going to be 25 minus 5. Plugging in 1 is going to be 1 minus 1. And we get a final area, if you want to add your units squared, 20 units squared. So at any time we want to find the area under a curve to the x-axis, we can use our definite integral to find that. So find the area enclosed by the curve y equals 15 minus 2x squared, the x-axis, and the lines x equals negative 2 and x equals 2. First of all, what does 15 minus 2x squared look like? Tell me some things about it. It's going to be concave down parabola. Do you know where the vertex is? 0, 15. I mean, if you wrote it like this, it might be easier to see that. That's a little bit more like, and we know that it's going down. Could you tell me where these x-intercepts are? You can even tell me is a not nice number like the square root of a decimal if you'd like. Something comma 0, something comma 0. Negative, this one will be positive. I'm going to tell you the square root of something. If you had to solve for x squared, move the 15 over, divide by 2, then square root, can you see that these could be 7.5s? Now, the reason I wanted to find out what those were is so that when we labeled 2 and negative 2 on here, I wanted you to see that 2 is going to be before the square root of 7.5. And negative 2 is going to be to the right of negative square root of 7.5. Why? Well, square root of 4 is 2. And square root of 7.5 is bigger than square root of 4. The reason that's important is we now know that this area, bring out the crayon. Oh, I'm going to go mustard color. Nice. Oh, pure relaxation. It even gets darker when you do it like, and yet it's still, you know how with crayon you seem like forever you're going in a spot, it never really gets completely dark? It does that. It's so nice. Okay, so there we've got our colored in part. And if we want to find that integral, well, now that's just the area from negative 2 to 2 of 15 minus 2x squared dx. Doing our integral here, it'll be 15x minus 2, add 1 to the exponent and divide by that number. Plug in our top value, so 15 times 2 is 30, minus 2 cubed is 8. This will be 16 over 3. And then plugging in negative 2, this is going to be negative 30 minus, plugging in the negative 2, this will be negative 16 over 3. And so when we subtract them, you get 30 minus a negative 30, that's going to be 60, and negative 16 over 3 minus 16 over 3 will be minus 32 over 3. If you get a common denominator, this will be 180 over 3 minus 32 over 3, 148 over 3. So here we're doing these questions without our calculator. Of course, if you're wondering after you've done one of these, have I done it correctly? Well, you can go to your calculator. You can type in 15 minus 2x squared, right? You can graph that, go zoom 6 to standard window. It's not going to all show up because it goes higher than that, but then you can do second, calculate number 7 for your integral from negative 2 to 2, shade that in, and did we get 48 over 3? Is that, well, we have to check, right? I'm going to, whenever you solve something on your graphing calculator, watch this. See that the answer was 49.33? Yeah, watch this. It's not going to work. Okay, I'm going to quit. I'm going to just push X and see what happens. Oh, it didn't work. Sometimes it remembers the number you just calculated. Sometimes it doesn't, like right now. Anyways, if you wanted to do it to get your number in here, well, we could have done math number 9 and gone from negative 2 to 2. And I'm sure there's a way I can steal that answer that I had from my calculator graph into here, but I can't think of it right now. I'm not going to spend 20 minutes trying to figure that out. But we could just have done it this way, minus 2x squared dx. Got our answer there, and then hit math, fraction, to see if it was 148 over 3. And it is. So over the next little bit, you might want to bring crayons to class. Just saying. Find the area between the curve of cos x plus 1 and the x-axis from 0 to pi. How do you graph cos x plus 1? Well, it would have a sinusoidal axis at 1. It would have a maximum at 2, a minimum at 0. It has a period of 2 pi, so if you wrote 2 pi and split it into 4 equal sections, cos starts at a maximum, then goes to the middle, then to a minimum, then back to the middle, back to the maximum. So here is the cos graph that we're looking at, and we want to find the area between 0 and pi. Sorry. Very nice. So, I mean, thinking of this from before we learned integrals, there's like no way we could think about how do we find that area of that shape. It's all curvy. It's kind of, I mean, maybe I would use a triangle for an estimate because it looks kind of like a triangle, but not quite. Well, now that we have integration, this is just the definite integral from 0 to pi of cos x plus 1. The integral of cos is sine. The integral of 1 is x. So we'll have something minus something. You plug in pi. Sine of pi is 0 plus pi minus, plug in 0, sine of 0 is 0 plus 0. And it's just equal to pi. Very cool. So we've talked about this before already as some of the properties. If a function is below the x-axis over a certain interval, we saw that the definite integral would also be a negative number. And that negative sign is just telling us that the area is below. It's still giving us the correct area. It's just giving us the area below. Now, if we were looking at a function that some of the area is above and some of the area is below, and you just did the integral from a to b, those areas are going to cancel each other out. So sometimes if you want to find the actual area between the curve and the x-axis, you're going to have to separate it by what's below the curve and what's above the curve. In order to do that, you're going to need to find your x-intercepts. So here's our first example, x squared plus 4x. Do you agree that that's a parabola that's going up? Can you see that you have x-intercepts at 0 and minus 4? How did I find that? Just by factoring. Where's the vertex going to be? Somewhere. Nice. Negative 2, comma 2. So if it's at negative 2, comma 2, then my parabola is going down. Does that look like a down-going parabola? Ooh, I like that. Down-going. So then maybe everybody agree it's going to be somewhere on this, and we just have to figure out how far it goes down on here. How do I figure out exactly where that is? -2, comma. Well, I could just plug in -2. What happens if you plug in -2? You get 4 minus 8. So you get -2, -4. This parabola is going up. And we want to find from -2 to 0. Pull out the crayon. Let's go red. Oh, beautiful. From -2 to 0. So what we're going to find is if we do the definite integral, we're going to get a negative answer. So I'll write it out. This is the integral from -2 to 0 of x squared plus 4x dx. If I do that, because that area is below, that answer is going to be negative. The question is asking us to find the area. There is no such thing as a negative area. It doesn't really make sense. You can't live with in a house with an area of -50 square feet. Just doesn't make sense. So when we're trying to find the area between that and the x-axis, we just have to say, well, I'm going to put absolute value bars around this. That's going to make it positive. So if I calculate this all the way through, I'm going to add all the absolute value bars right at the end. Still going to do my work. I'm going to go from -2 to 0. I'm going to integrate. So this is going to be x cubed over 3 plus 4x squared over 2 minus, and you'll get 0 plus 0 minus, this is going to be -8 over 3 plus 16 over 2. If I do this, get a common denominator here over 6. This is going to be -24 plus 48, right? -24 over 6 plus 48 over 6, which is going to equal, still have a minus sign out in front, -24 over 6 or -4. Did I make a mistake? It's not 24. Oh, because I multiplied by 2, it should be 16. Thank you, right? There we go. And then -16 plus that'll be 32 with the negative out in front. We'll give this -32 over 6 or -16 over 3. Which is what we expected to get a negative answer. And this is how it's often going to be. You're going to do all your work and go, oh, I got a negative answer in the end. So how do I show my work correctly? I go, oh, I'll just go back, add absolute value bars, add absolute value bars. Keep adding absolute value bars until I want to actually apply them. And the area is 16 over 3, some sort of unit squared. So if our area is below and it's asking us to find the area, then our area needs to be positive. This is different than if it just said, calculate the definite integral from -2 to 0 of this, because then we would leave our answer as negative. Because the definite integral is negative in this case, indicating that that area is below the x-axis. But if it's actually asking us to find the area, then we'll need to make sure that it's positive in the end. And I did 2 to 0. Now we're going to, do you have this from -2 to 2 on yours? Okay. So now it's going to be the same graph, So I'm just going to go back to this graph, but now we're also figuring it out up to 2. So we'd have another section that we could color in. I used red last time. This time I'm going to use green. And the question is still saying find the area between the curve and the x-intercept. I mean the x-axis. So if I just did the definite integral from -2 to 2, I'd get the wrong answer because my positive area and my negative area would cancel out. So what I need to do is I need to recognize that there's an x-intercept at 0 and say the area is going to be, the area is going to be, it's still doing it. It might get annoying if I did the whole question in crayon. Yeah, okay. -2 to 0 of our function, which was x squared plus 4x. And then we'll have to add from 0 to 2 of x squared plus 4x dx. And we already knew that this section was the negative section, so that part's going to get our absolute value. Since we already calculated this part, is it okay if I just write that as 16 over 3 to start with? Yes? And now we're going to have to add, well, this is still x cubed over 3 plus 4x squared over 2 from 0 to 2. So we'll get 16 over 3 plus, plug in 2, 8 over 3 plus 16 over 2, minus 0, 16 over 3 plus 8 over 3 will give me 24. 24 over 3 plus 8, which is equal to 16. So as far as working with fractions and mental math and doing calculations quicker, did you see that instead of trying to put these two together first because they had different denominators, these ones already had the same denominator, I added those together. And then I noticed, hey, 24 over 3 is a nice fraction. That's just 8. And 16 over 2, I could write that as 8. So that made my mental math a little bit easier to work with. Here we have an x cubed graph. For our x cubed graph, it could have some parts above and some parts below. In order to figure that out, we need to be able to draw a quick sketch of this. And we're not going to use all of our calculus techniques to do a sketch because that might take a little bit of time. What are the key things that we need to know for our area? We need to know our x-intercepts. How easy is it to find our x-intercepts? Can you factor that? Well, there's a common factor of x, leaving me with x squared minus 3x plus 2. X minus 2, x minus 1. So we get 3 x-intercepts relatively easily. We know that it's at x equals 0, at x equals 1, and at x equals 2. This is an x cubed graph. What do you know about x cubed graphs? Positive x cubed graphs. Do they start here going down or here going up? They start going up. So this graph is going to do something like this. And our x-intercepts make our graph go into three separate things. We're going to have colored in brown. Very nice, this little section. In the red, we have that little section. And then back in the positive, we would have this section. So we are going to need to calculate our integral 3 times for 3 different parts. So our area in the end is going to equal the integral from 0 to 1. And instead of writing x cubed minus 3x squared plus 2x dx each time, are you okay if I do y dx? So I'm still integrating with respect to x, but instead of having to write the whole function, the function was equal to y. That just makes it a little bit less to write. Plus, we're going to need to do the area from 1 to 2 of y dx. But what do we know about that area? Well, we know that it's going to be negative. The way that I drew it, it does definitely look like it's going to be the same, but it doesn't have to be. And then from 2 to 3, that's going to be another positive area. So our sketch tells us which parts were positive, which parts were negative. When we integrate this function, we're going to get x to the 4 over 4 minus x cubed plus x squared. So we have that from 0 to 1. Our absolute values are going to stay. We're going to have that same thing. From 1 to 2 plus, and the same thing, x to the 4 over 4 plus minus x cubed plus x squared from 2 to 3. At this point, we have a bunch of not very nice mental math to do. So instead of doing all of that mental math, I've got it pre-done for you here. No, that's too far. Here we go. So there's our picture from our graphing calculator. And doing each of those things. Again, if you were allowed a calculator on this one, which you might be because there is an x to the 4, which just isn't that nice to calculate with, then it is sure nice if you could find each of those areas quick with your calculator rather than having to do all that mental math and getting your answer. So yes, it did happen to be perfectly the same. They're both a quarter above and below. And when you add them all together, they'll all be positive, so you get 2.75 units squared.